Hello, and welcome to Science Streams. And I'm happy to introduce you to Kieran, who is an earthquake specialist and seismologist. And I'm happy to have this conversation tonight. Um, and hopefully, uh, we're going to have a wonderful time. So, Kieran, why don't you tell us about yourself?
Sure. Yeah, so my name is Kieran. I have a bachelor's degree in physics from the University of Montana. And then when I was living in Montana, I really liked science and I really liked physics, but I really also enjoyed being outside. And most of the work that I was doing when I was in undergrad was in a laboratory, and that wasn't really for me. And so I wanted to figure out what else I could do. And I was working as a physics tutor at the time when I was in undergrad. And a lot of my students, when I was tutoring, were geology majors because the geology majors had to take physics, and a lot of them needed a little help. So they started telling me about this thing called geology, which I had never really heard of. and I just kind of understood at that time that I could do physics maybe that was related to geology, and that was this topic called geophysics. And so I ended up going to grad school at the University of Colorado in Boulder, and I studied geophysics and mostly seismology, but I did do some other areas of geophysics, and I defended my PhD last year. And I had been working at the Colorado Geological Survey for a couple of years since 2018. So when I graduated, I started working full time with them. And I'm mostly in charge of managing our seismic network and doing some other seismic research type activities. Um, but we are a government agency, so we do a lot of outreach and education, and it's a pretty good place to work.
And we appreciate that. And Carla, who is a teacher friend of mine, just followed. So I'm happy to have
Nice.
her here listening in. Um, and I got, so many, questions for you. I have been to Boulder uh, once.
That's where I'm
So
sitting.
um, part of my family actually lives in just outside in Sheridan in Colorado. So
Mhm.
I've been there before. And there's lots of nice mountains. And it's
Mhm.
much more geologically active, I think, than New York, if I'm not mistaken.
Well, yeah, I'm not super familiar with what's happening in New York. I know you do get earthquakes on the East
Yes, we
Coast
do.
though, but
We do.
it's not really an area I study, so I'm not so I will say that the like mountains here in Colorado, the Rocky Mountains, it's a much younger mountain
Hmm.
range, so it's
Yep.
formed by much more recent tectonic history than the East Coast mountains.
Yep. And I like how you kind of, I had the same experience. I think a lot of people in science kind of had the experience of making that decision or feeling whether they find their place at home in the lab or outside or somewhere in
Mhm.
between. Because I tried
Yeah.
both extremes and I didn't like either. So I ended up as a teacher because I was like, if I want to take my class outside, I can. If I don't want to,
Uh-huh.
I don't have to. Um, so I find that interesting. You kind of went through that journey, I think, that a lot of us go
Mhm.
through.
Y- Yeah, in part, I didn't really have the patience for a lot of the lab work where you're kind of like, okay, you got to turn the knob a tiny bit, and then you turned it too far, you have to go back. So,
Yep. And I was thinking, I saw something, I think it was on, I can't remember if it was on Discord or Twitter about people having to access, the seismographs and the equipment, and they're being in remote places and being expensive to do so as well. And it's basically
mhm.
labor intensive. And that's kind of what you were talking about. So I'm I'm interested in that part of the outside in particular. Um,
Yeah,
like how remote are these places where you put, can you talk about the machine itself and then I guess
sure.
where they go, how hard it is to get to them, and how often are they protected by bears?
Yeah. So in Colorado is where I have experience in that, so I can speak to that. There's definitely stations that are in much more remote places. Like I know some of the seismic stations in Alaska you can only get to by helicopter. So in Colorado there are other seismic stations, but the Colorado Geological Survey, so those are the stations that I maintain. We call those stations, or we call like different groups of stations are considered called usually like a network. So I operate what's called the C0, like C is in Colorado, C0 network. So the C0 network has 8 stations in Colorado. I can show you where they are on a map if you're interested, but just I can actually show you pictures of what they look like if you
Yep,
want.
we could do that. And at the same time,
Let me
someone redeemed I'm a banana, so I'm going to be a banana for a moment. Now I'm a banana for a moment.
That's impressive. I don't know if I have the turn into a banana skill, but
Yep.
let's get this little station map. All right. How about how about this? Mm. Can we see these guys?
Hold on one moment. And here you go.
Okay. So these are, at least at the time I made this map, all of the seismic stations that I knew about in Colorado. It's possible there's a few raspberry shakes around that I didn't put on this map, but each color represents a different network. So my network is the dark blue ones. And so I have 8 stations. And so you can see, even just from looking at this map, that a lot of them are near some kind of road. So all of my stations I can drive to, but some of these, like this station and these two, are definitely a ways out there on dirt roads. Um, so this station right here, this is probably what I would consider my most remote station because it's a good 40 miles on dirt roads away from the nearest paved road. Um, but it's on MCSU, or it's called MCSU, that's its name, but it's on the CSU, so it's on the Colorado State University's sort of field campus. So once you get there, it doesn't feel as much like you're in the middle of nowhere because you're on their campus. So they actually have satellite internet, you can get on their Wi-Fi, but just getting there is pretty remote. Um, this station down here is also very remote. This is by Creed, Colorado, but it's located on someone's ranch. So it's a very rural, very remote area. But most of the stations, I still have cell service. This one is an exception, and this one is an exception. I don't even have cell service at those two. So those two
Hmm.
are probably the most exciting ones to travel to, just because if anything goes wrong, um, I can't call anybody. So if you want to see what a
Yep.
station looks like,
We have
I
a couple. We
can.
have a question as well, and
Sure.
you can do both at the same time. Carla wants to know: do you make decisions on where the new sensors need to be, and do you ever
Yes.
move them?
So, yes, I do make decisions on where the new sensors need to be. We have, and a lot of that is based on. I could spend a lot of time talking about that. A lot of that is based on where we have earthquakes in Colorado, because my network is mostly designed to monitor earthquakes that happen in Colorado. Some networks are designed for more global seismology.
Hmm.
So, that being said, I can pick up global earthquakes. Like, I can show you the earthquake from Japan, for example, on a seismic station in Colorado. But when we deploy our seismic stations, we focus them on areas that are prone to earthquakes in Colorado. So, a lot of their locations are related to that. And then, as to whether or not I move them, I've moved one. They have a lot of infrastructure, and there's concrete and there's holes and there's towers, and they're not very this type of station that we have, it's not very fun to move. Ideally, they will be in the locations that they're in forever. That being said, there are different kinds of seismometers. We like have a whole subset of seismometers that we would call portable seismometers, and those are designed to be moved very easily. So you can install them much more easily. They're lighter, they're smaller, they don't need as much infrastructure, and they can move more easily.
Are they not as sensitive, or they're made
It
out of?
depends. It depends more on some of them are not. Yeah, some of the instruments are not designed to be as sensitive or they're not as fancy. Um, a lot of times the infrastructure for installing them really changes the quality of your data. So, for example, if I just dig a hole in some soil and I just dig 2 feet deep and I just drop a sensor in there, the soil shakes a lot, so you're going to get a lot of sight effects versus if I dig a really deep hole and I put concrete in and I make it a really well insulated vault. You're going to have a different kind of data quality
Mhm.
than the just dropping it in a shallow hole.
Right.
Don't ever drop your seismometers.
From experience, I take it that comment.
Yeah, so I can just show you, this is just like a little picture of what the actual sensor looks like inside the
Yeah.
ground.
I want to make this a little bit
So
bigger.
I'm sorry?
I'm going to make it a little bit bigger.
Yeah, this is the picture.
There you go.
So you can see that there's concrete down here. It's on this glass plate that's been polished. It's in this is what we call a vault. So this helps keep moisture out, and the cables go through this conduit to our to the rest of our equipment. But just yeah, a couple of things. There's a north arrow. So a lot of seismometers, you're measuring ground motion, but you're not just measuring ground motion in one direction. You're measuring it in three directions. So that's usually vertically north, like north south, and then east west. So that's why you have a north arrow on here so that you can orient
Hmm.
the north component to north. And yeah, so this is sort of like, I would call this a mid grade quality of seismometer. It's not like a cheapo temporary one, but it's not like a very super fancy um,
Hmm.
deep burial seismometers. So these are kind of your mid tier.
Cool. So, Chad, the alpha male, welcome in. We're not talking about climate change this week. We're going to be talking about earthquakes. And Carla, that project, I was going to, you mentioned that on Twitter, and that tsunami project sounds really cool. Um,
Hmm.
and Volcano Doc asks, how much does it cost to install a seismometer and maintain it annually?
That's a great question. Well, it can vary so much on the
Hmm.
seismometer. Like, can I? Are you still sharing? I'm gonna.
Yes, I'm still sharing. I can stop if you
Okay.
want.
Yeah, we don't. I don't think
All right,
we
hold on.
need. I,
Give me a moment. All right,
it's
there you go.
just funny because I can't see you unless. All right, here we go. Okay. I was gonna close my window and then you'll see my whole desktop. Okay, so it depends a lot. like I think I mentioned Raspberry Shake. I don't know if any of the viewers have heard of a Raspberry Shake before, but it's actually a really cute little tiny what we call a geophone. So a geophone is sort of the basic um kind of most simple electronic seismometer you can get. They're pretty robust, but they aren't very sensitive to different to broadband frequencies. They're sensitive to high frequencies, and I think those cost $1,000 or so, maybe two. It's like a citizen science tool, so you
Hmm.
can buy one of those. It's completely self-contained, and you can put that in your classroom or in your basement, and that's a seismometer.
Now,
And all you have
I guess it's since it's Raspberry Shake that it's based on Raspberry Pi.
It is, yeah, so the
Okay.
computer that you get with it is a little Raspberry Pi computer, so it's a basically, it's a tiny geophone, or usually 3 geophones, because you get the 3 different components,
Hmm.
and a little Raspberry Pi computer with an extra board on there that, communicates with the geophones,
So
and all you have to do
it's
I'm
slightly
sorry?
better than the accelerometer on your phone.
Yes, slightly better. It's a step up from that, but all you have to do with those is plug them in, put them on the ground, and you're good to go. And
Hmm.
then there are, like I said, some of those portable seismometers depends on what they are, but some of those could be, maybe in your five to $10,000 range. The seismic stations that we put in are probably more in the $10 to $30,000 range, and that's for all the equipment. So I just showed you the seismometer itself, but
Hmm.
every seismic station also needs to have a brain. It needs to have like a computer system. So usually that is a combination of a digitizer and a logger, but sometimes those can be separate equipments. Um, and digitizer, I guess I think that what that does is kind of interesting for the uninitiated. um, the way that a geophone works fundamentally is you have a coil of wire and you have a magnet that shakes inside the coil. And when you shake a magnet, when you move a
Hmm.
magnet inside of a coil of wire, you induce a current in that wire. And so basically all you're getting is this electrical signal, ground motion translated into electrical signal. So what a
Hmm.
digitizer does is it takes what's a continuous analog electrical signal and it'll give it a value at discrete points. So you have a digitizer and a logger. So I'm giving you prices for what I would say is like, a full
Hmm.
station. A really nice, like what the kind of most modern form of seismic stations are called post-hole sensors. And so those are where they drill really, really deep. Like my sensors are maybe 1 to 2 meters below the surface. These ones are like 10 meters below the surface, and they're skinny and they're small and they go down into this post hole, and those ones are definitely 50,000 or more.
Um, yeah, so that's expensive. Carla was asking again about the Raspberry Shakes. I put the website in there. I just looked at it myself
Mhm.
because this does look like something really cool to work with kids.
Yeah.
Um,
Yeah, we have one. I have one at CGS, and I use it a lot for outreach. Like it's really good for like bringing to classrooms and doing live demonstrations. So I can like bring the Raspberry
mhm.
Shake and plug it into my computer, and students can watch the wiggles in real time. So you can stomp on the floor and you see the
Right.
signal.
And I was
Yeah.
thinking of other projects such as we have a lot of truck traffic, which has been a problem in the city where I work, and so
Mm-hmm.
you could use those to read out, the shaking caused by trucks down
Yep.
residential streets as well.
Mm-hmm.
So that's another interesting thought. Oof, I'm thinking now. Um, and yeah, I think I know that when I've done Raspberry Pis, it's all in Linux, so I have to like, brush
Yeah.
up on my Linux when I use it. But having never
So the
done
res
Python, I don't know.
The Raspberry Shake itself is pretty user friendly, even if you don't know Python. It's pretty easy to take out of the box and plug in and get going. They have good documentation for it on that website you sent. And also there's a web interface to communicate with it. So even if you don't know any Python or any Linux at all, unless
Mhm.
something goes wrong, you can pretty much just use their web interface to talk to it.
Usually, when I've done with Raspberry Pi before, you just basically you type in the code into the command line, get this, and it goes
Mhm.
out, it grabs the program, and then pops it on your Raspberry Pi, and
Mhm.
it runs itself almost.
Yep.
Um,
Yeah,
so,
so it's kinda like that, except you don't even have to do the get this part. It already comes with
oh,
it.
it already comes with it. Wow. See,
Yep.
even better. Awesome. And then the part about Volcano Doc asked about maintaining it, because
Okay.
that has to be a cost as well. Not just send a bunch of grad students there to do it.
Yeah. So, yeah, so most of what goes well, okay, so there's, I guess, a couple of maintenance costs. We have all of our stations are telemetered. So that means that they're sending out their data to our computers in real time. And most of them run on cell modems. So they all have their little cell phone plans. I think all of our stations that are on cell phone plans, I think all together they're about $200 a month.
Hmm.
We have two stations that don't have cell service, and those ones use satellite internet. Satellite internet is way more expensive. I think it's almost over $200 a month for a single station to
Wow.
have satellite. The other thing that's kind of annoying about satellite is it takes a lot more power. So all of these stations are off the grid. They all run on batteries and solar panels, and the if you have to run your satellite internet off of a battery and a solar panel, you need a lot more batteries and a lot more solar panels
Hmm.
um, than the ones that run off cell phones. So those are just like regular, like we're always going to pay for that. In terms of maintaining them, it's really all or nothing. I feel like that's a big part of my job. So it costs my time to maintain them, and because we're in Colorado, is a big state, I do a lot of driving in the summer. But we're not taking helicopters, so I guess that helps. But there's gas, there's my time. For the most part, we've had pretty good luck with our equipment. A lot of times we're replacing batteries and solar panels more than
Mhm.
anything else. Um, I've really only had one sensor that is in need of repair, and I don't actually know what that cost is going to be yet, so I'll find out. But
I all I can think of is it's all fine in the fall, in the summer even, or
Mhm.
the spring, but in the winter, or even in the spring when there's or when like the rocks start falling, right? Some I know in
Mhm.
Colorado, some of the roads become impassable.
Yeah.
Um, and those can be really difficult. You kind of like plan to go out there like end of fall and kind of check on it to make sure it's okay, and then just wait all winter and then go back in the spring and see if it's okay.
That's exactly what I do. I have, because the stations are telemetered, I do have some sense of like how they're doing when things
Hmm.
aren't if something's not working. I'm like, okay, well I can see what the battery voltage is, and I can say like, oh, well maybe the battery's not charging, or maybe this battery's gone bad. But one thing that has a tendency to not work sometimes is the telemetry system itself. And that's always frustrating because all of a sudden I just won't be able to talk to a station, and I won't really have any information about what's wrong with it. I'm like, did it get struck by lightning? Did it, I don't
Oh wow.
know. And so then I'll have to drive out. But yeah, I mean, at the end of my field season, so this last year, because it was my first summer working full time at CGS, I did a lot of upgrades on the station where I was just changing out cables and rearranging things and just kind of cleaning them out, literally sweeping dirt out of them. And so at the end of the fall, I visited every station and did a little bit of upgrades, made sure they were all okay. And then, yeah, I've spent the winter just crossing my fingers, being like, I hope they're fine. Cause a lot of these I can't get to in the wintertime. I
Mhm.
can't drive to them. I can't hike to them. I could maybe snowshoe, but
Now it's I mean, you're obviously paid to do this, right?
mhm.
Is there like a crew that inspects these? And I assume it's similar not just for Colorado, but each state and then, the federal government has their own people that
Mhm.
that go out as well. So,
Yeah, so the federal government has their own, so the USGS, the United States Geological Survey, they have their own networks. They have multiple networks that they run. And so they do have a team of people that does work on their networks. For Colorado, it's just me. I'm the only full-time employee. That being said, if I need help, if I'm like, oh, can somebody come out with me? We have a contractor, a guy named Howard, actually, who works with us, and he works with a couple other states. Like he works with Arizona and New Mexico. And I call him like Seismic Lazarus because he raises all the stations from the dead. Like when no one else can fix them, he can. So we contract him. Sometimes I can get other staff in my office, but we have a small, like the Colorado Geological Survey, we have about 20 employees. Um, some states have 20 people just working on their seismic networks. Like I'm
mhm.
sure California and Washington and other places will have bigger seismic staff than we do. Um, but yeah, and there's also, I think, there's a lot of collaboration and just favors of goodwill. Like the USGS has offices in Golden. We actually both have offices across the street from each other, and so they have helped us out with things. And um, the idea being like us having our seismic stations up and running is good for everyone in the scientific community. And everyone else's seismic stations being up and running is also good for me. So we sometimes will help each other out if we can.
I can't imagine. I mean, it sounds like a lot for one person, but I'm not the one doing it. And
Yeah.
um, so I have is feel free if anyone's in chat and you have questions, put them out there, and we'll get to them. I got plenty questions of my own prepared ahead of time. Um,
Mhm.
so well, about the solar panels for it. How easily does weather destroy or damage them?
So solar panels are incredibly robust. The only problem I've ever really had is there's one station that's in um it's basically surrounded by farmland, and that solar panel has a tendency to get really dusty. So a lot of times I just have to go out there and clean it with
Hmm.
Windex. but but it normally continues to work. But yeah, the electronics behind a solar panel are pretty simple, and so they're pretty tough
Hmm.
little pieces of machine. And also we get a lot of sun in Colorado, so they're a pretty reliable way to get power.
Yep, sounds good. Um, so what kind of things do you sense in Colorado? 'Cause I mean, it's not a real earthquake prone area, I don't think. I mean, are there,
Mhm.
uh,
Yeah, well, we do have earthquakes in Colorado. A lot of them are small magnitudes, so that would be, like your magnitude 2.5 or below. Most of our earthquakes are, and so we can sense them with the instruments, but you wouldn't feel it. Like I said, we do also get earthquakes from all over the world. You can see our instruments are good enough that you can see global seismology. And because Colorado is pretty remote in some places, sometimes those stations can be really useful for locating earthquakes on the other side of the earth because we don't have a lot of local noise on the sensor. Um, so we do, I guess their primary function is for earthquakes, but there's a lot of other things that you can see on a seismometer. You can see trucks, like you said, you can see traffic, you can see things wandering around. One thing that I think is really cool that you can see on a seismometer is you can see the ocean, even in Colorado. I can see there's a very specific band of frequencies that the ocean waves operate at, and I can see that noise, the
Hmm.
ocean noise, on our seismometers in
Wow.
Colorado. Hmm.
That's, I mean, but you were saying before that different seismometers have different sensitivities, so you can't
Yep.
see them on all of them, but you can on specific ones you can see them. Okay.
So the yeah, I can see noise. I do. I literally see the noise because they're wiggles. um yeah, so different seismometers have different frequency bands that they're sensitive to. So I do like to use analogies with sound a lot, but the way that you have high pitched noises that are high frequencies and low pitched noises that are low frequencies, seismometers run the same way. And so that also means that earthquakes have different frequency bands that they're strongest in. So, for example, like one thing that I kind of like to to um, I guess a good example. So, attenuation, I don't know
Hmm.
how familiar people are with that word, but attenuation is just how your amplitude decreases with distance, right? So as your wave propagates through something, its amplitude diminishes. So a sound will sound quieter to you if you're farther away from the speaker, right? But different frequencies also attenuate differently. So the example that I always give is like if you're walking up to a concert, you hear the bass first. And then as you get closer, you hear the rest of the sound. And it's not because the bass is louder, although it could be, but it's because the bass attenuates less. So the lower frequencies travel farther away. So, what that means in terms of earthquakes is earthquakes operate the same way. If you're close to an earthquake, you'll have more high frequency content. If you're farther away, you have more low frequency content. So, the range at which your seismometer is sensitive, what frequency range, really has to do with how what quality you're going to get for closer or farther away earthquakes. So, with regional earthquake studies, like if I want to look at earthquakes that are really close by me, then I'll use high frequency sensors. If
Hmm.
I'm studying teleseismic, so that's what we call when they're really far away, then you'll use sensors that are more sensitive to low frequencies. What we deploy with CGS is called broadband. So those are really instruments that kind of can do it all. They are sensitive to a very wide range of frequencies, or a broad band of frequencies.
Volcano Doc asks, did you record the HTHH lamb wave? I don't know what that means.
I don't know what that is either.
So maybe she can describe that for us. Um,
Too many letters.
um, the Tonga eruption in your instruments.
Oh, yes. Yes, I did. So we saw that we didn't see that as I'm not exactly sure because I'm not used to doing volcanic seismology, so it was sort of a new thing for me to look at. But the signal that I think that I saw on our seismometers was actually from the pressure wave, so not the ground motion from the initial eruption, but whenever you saw those videos on the internet that I thought were really cool, showing the big shock wave going through, so that pressure wave is what we saw on our sensors. And
Wow.
we have both underground sensors so we could see the pressure that traveled through the ground, but we could also see, I also have just barometers at a couple of the stations just because some of them are co-located with like environmental sensors. So you could also see the pressure wave in the air, which is pretty cool.
Really?
Yeah.
Huh.
Yeah.
Wow. That's got to be a sensitive barometer.
Yeah, well, it was actually a really strong signal. It is a sensitive barometer, but a lot of like weather stations could
Huh.
see the pressure drop when
Wow.
that pressure wave came through. Hmm.
Yeah. That's crazy to think about that.
Yeah.
Wow. That's that's really interesting.
Yep.
Because like I don't know. I never thought of that. I mean, it's like, yeah, it makes sense now that I think about it that, it would
Hmm.
travel through the air and you'd be able to sense that, especially if it's a really strong wave like volcano oxides, but you know, I never thought about it.
Yeah, I didn't either until it happened, it was like once that eruption happened, I saw the pressure wave like on, the internet. And I'm sure somebody else had thought of this, but it was like, oh, well, let's look at the barometers. And then I noticed on like Twitter, the weather station, all the weather people were like, look, you can see the pressure drop in the air. And I was like, oh, I should look at our barometers. And I could also see that signal.
Yeah. Cool. Yeah, Eagle
Hmm.
Scout Survival Tips. Thanks for stopping in. I'll see you later. Um, and this lends to the next part where we were talking, or you mentioned what even when we first started communicating about X-rays, of the Earth, right, and
Hmm.
seeing the interior of the Earth. And
Yep.
I always when I
Well,
when I when I talk to my students, I often use that as a great example of inference where no one's actually seen the interior of the Earth,
hmm.
but we can infer what it's like based on, you know, seismology, you know,
Yep.
and so do you want to talk about that? Because I'm kind of curious. I mean, because I
Oh,
see
I thought you'd
graphics and
never
how the
ask.
waves, I've seen the pictures of how they go through the earth and supposedly show that it's, more liquidy versus solid. But yeah, I mean, how
Yeah.
does it exactly work?
Okay, well, we can talk about a couple. Let's start. Let me get something up and then you can share my screen. I'm going to actually start by talking about a CT scan. So, let's look at all right, here we are. You can share my screen.
All right, let me adjust this a little bit. So this is a CT scan, kind of.
So yeah, well, the first thing I'm going to talk about is a CT scan. So I think CT just stands for computerized tomography, which
Hmm.
is to me a not very good descriptive term because computerized just means a computer, and tomography applies to what I do, like seismic tomography, as well as like tomography of the human body. But in any case, like the way that a CT scan works in the medical field is you have you go through a slice of the body. So usually with a CT scan, if
Hmm.
you want a 3D image, you'll need to go through a bunch of different slices. But you basically have an X-ray source on one side and a receiver on the other. So that's what all these little red lines are representing as your X-rays. And then if we look at that slice from above, so let's say your slice has, this is just really simple
Right.
drawing, but like let's say you have these dense bodies right here, like all the shaded areas. So remember this idea of attenuation that I said was talking about earlier. So if the amplitude of your X-rays attenuate, when you go through the dense bodies, and you can see that for this long dense body, you're going to have really low amplitude when you get to your receiver. And then for these guys over here, like through this body and this body, you're having some attenuation, but not as much. And then the areas where you have no dense body, you're not attenuating. So the idea behind a CT scan
Hmm.
is to use this little attenuation function over here to locate where your bodies are. And so the way that so here's your little plot. But this is just for one angle, like going in one direction through your slice. But
Hmm.
what they really do is they rotate the receiver and the source around your disk like this, and you get those kind of plots, those attenuation plots, in a whole bunch of different directions. And so this really helps you um, kind of understand how where your dense bodies are, because you're going to be constraining them from a bunch of different sides.
Hmm.
So, like, if you have a donut, if your body's shaped like a donut, you might have
Hmm.
you'll have uniform attenuation, and then this little um, bump in the middle. And you can imagine that no matter what side you go through, you're going to get kind of that same plot. So if all of your attenuation plots look like this, then you know you have a donut. So that's like a very simple example of how CT
Hmm.
works, and we can unshare now.
Okay. Let me give you one moment.
I just had to show you my drawings.
Yep. Very nice drawings.
Thank you. I did them all myself.
Yep.
Are we unshared?
Yep. Yep.
Okay, so with seismic tomography, it works a little bit differently in that you can do an attenuation study. So that is one way you could just look at the amplitudes and how they change when they pass through the earth of your seismic waves. But another thing that we can do in seismic tomography is we can look at the travel times.
Hmm.
So if I have an earthquake in Japan, the speed, or the time I should say, that it takes those earthquakes, those waves, to arrive at my stations in Colorado will be dependent on what the material is that the waves travel through. So they'll travel differently through dense material compared to non-dense materials. So that's kind of a proxy, well, for rock type. So we can figure out what the compositional material is, as well as temperature. So the temperature affects the seismic wave speed. Um, and there's a lot of different ways that we can do that, but unlike a CT scan, we don't have control over the earthquake source. And not only do we not have control over it, but we don't always know exactly where it is. We're pretty good at knowing where they are, but there can be some uncertainty even in the earthquake source location.
Hmm.
So there's two kinds of seismology, where there's passive source, which is when we just wait for an earthquake to happen, and then there's active source. And so active source is used a lot in experiments, and so that is where we do control the source. So we could use dynamite, or drop a big weight, or
Hmm.
use an air gun to create the seismic source of energy, and then we can obviously control where our receivers are. um, so that's kind of how those two concepts are similar. But yeah, like an X-ray of the earth, we really are getting a lot of that information just from the surface. We can't drill a hole in and double check and see if we're right. If we said, oh, I think there's granite under here, it's like, how deep can you drill? Not very
Not
compared to the
very.
earth.
Right. And it's also, I want to, this is my earth science knowledge of your primary versus your secondary waves, will travel, how they arrive will also tell you what they're going through as well. Correct?
So yeah, so a lot of times we look at the difference in the travel time between those two waves. So P waves, which are the pressure waves, those travel faster, and then S waves are the shear waves, and those travel a little bit slower. So even just by looking at the difference between those two travel times, you can get a sense of how far away your source is
Hmm.
when they're farther apart, right? If the travel time difference is greater. There's also an there's also it's also a property of the rock, the
Hmm.
relative, like the ratio of those two speeds. So we actually call that like the VPVS ratio.
Ooh,
So
fancy.
that can change depending on the temperature and the composition.
Okay. And Yeah, I remember. Maybe someone in chat remembers this. There was this thing where like they tried to get like 10,000 people or like to jump at the same time and see if you know they could feel it around the world or whatever.
Hmm.
I heard it was a
Yeah,
failure.
that's always a little demonstration I like to do with the raspberry shake is get everyone to jump.
Yep. And you know, the other thing you can detect are things like, you know, nuclear weapon tests, of course.
Hmm.
Um,
Yep.
but we don't want to use those as our control to actually find out if, those work.
No, but that's definitely a really important application of seismology is to like monitor um, the nuclear treaties. That's a big thing that the government does with those is make sure that people aren't testing nuclear weapons, and then um, they also want to know who is blowing things up and where. That's another important.
Hmm.
Hmm.
And so I think that what other, I mean, I know you don't do international, but other than the US, what are some other countries that, because there has to be a high level of collaboration for a lot
Yeah.
of this science, what are some of the other leading countries in seismology that kind of we work with to do a lot of this research? Can you speak to that
That's
at
a
all?
good question. I don't know exactly. I mean, I know that countries that like people that I know have worked with. Like, I know that Japan is a
Hmm.
good example. They have a ton of earthquake science research, and especially in tsunamis, they are that's like the creme de la creme. Places that have a lot of earthquakes, like there's a lot of seismic studies in New Zealand. Like New
Hmm.
Zealand is a very active seismic area. um yeah, I mean there's like different, and there is like a global seismic network. So we have, I showed you, we have a Colorado seismic
Hmm.
network. There is a global cooperation, and I know that there's just like a lot of, yeah, I think a lot of times people will even deploy instruments temporarily, and a lot of times we'll share that data. So we have like I can never remember what the acronym stands for, but there's a consortium, like a seismic consortium, that is they provide a service, and that is archiving data. So all of the data, when you want to keep it, it takes space on a computer, and a computer takes power and all that stuff. So
Right.
there's a consortium that will archive your data for you, and but then what they also do is share it. So we all work together to support this consortium to archive everyone's data, and then we also share that data across. Not every seismometer on the earth is in that archive, but a lot of it is. So again, like I said, the idea, um, I think, especially in seismology, is probably true in a lot of science, but sharing the data, because it is expensive to get. Um, so we want to make
Hmm.
sure we get as much out of it as we can, and that everyone else does as well.
Yep. And I want to get into that a little bit more, but Volcano Doc had a question. Is it true that nuclear tests were how modern seismology got started?
I don't know if it's exactly how modern seismology got started, but I would say it was a huge part of our technological advances in terms of
Hmm.
instrumentation. Yeah, there was I mean, like you can, and this is true I think with a lot of different technologies, but when you start looking at post World War II, that's when there was a huge explosion in terms of what
Hmm.
our technology could do.
Yep. Um, and I want to get into the data. Um, is there a place of a repository where we could get where teachers can get the data? Is there like a
Yeah.
free access?
Yeah, so like I said, on Iris, the consortium, all of the archive data there is publicly available and it's free.
Hmm.
So I can show you. If we go back, let me go back to my screen sharing. We're just gonna I'm gonna just show you the internet. I know it's a
Okay.
place you've never seen before. um, but yeah, there's a lot of cool things you can do. So let's go. Let me,
Let me know when you're ready.
all right, I guess I'm still here. I'm ready. So can you see these two windows
Yep.
of the
Let me
internet?
of the internet. Yep. All right. So we see the
Yeah. So
USGS.
this is the USGS's website. And so I just pulled up, this is called the event page. So this is the event page for the Japan earthquake that just happened. And if you wanted to look at the waveforms for that earthquake, there's a place on here. And so they're
Hmm.
actually usually getting data from Iris. So I pulled up the waveforms for my stations in Colorado. So you can see these are all online, and this is that earthquake across our my 8 stations in Colorado.
Hmm.
Um, this is the IRIS website. So this is the station in Hayden, and this is showing, if I refresh this, it'll probably update, but this is showing the real-time data from this station.
Wow.
So if you go to like iris.edu, so it's the Incorporated Research Institutions for Seismology. I guess I don't know if I can put things in the chat.
If you put it in our chat that we're on, I can then copy and put it into
Oh
the.
yeah, okay.
We
I'll
can do
do
it
that
that way.
because I think I forgot to actually log into my Twitch account, which I do have one, but I
Hmm.
forgot to log into it.
There you go.
All right, so so you can see data here, and I think it does get a little technical because their target market for this product is like other seismic scientists, but a lot of like smaller networks, like if you go to my website, like the Colorado Geological Survey.org, and you go to our earthquakes page. Um, like I put the data from all of our seismic stations, I put links to it on our website. So you can get the data for our stations. It's from Iris, but I put links to it on our website. So I think some like smaller government agencies would probably have something like that.
Hmm.
But for if you wanted to look at I think what most people wanna do is they wanna look at an earthquake, and so the best way to do that is to go to the USGS web page and then click the waveforms link, and so it'll say, "Oh, do you want the ones from Iris?" And that's what I was showing you over here. So this is just a
Okay.
plot, but you could also request the data and download it.
Wow.
Mhm.
Um, and I mean, is none of it's is it like raw data? I mean, it's literally the data from the
Yeah,
seismograph.
it's
So.
raw data. So I we didn't talk too much about this, but yeah, the data from the seismograph, remember it's a bunch of electronics
Hmm.
and also the physical properties of the instrument will affect how it records ground motion. So a lot of times, the raw data that you get on Iris, the units of your ground motion, what you think would be units of your ground motion, is actually counts instead of like meters or meters per second. And that's
Hmm.
because that's the units that the digitizer spits out. It takes your analog electronic signal and it spits out counts. And so to actually translate that to ground motion, you have to understand the instrument really well. So what we call that is like the instrument response. So for scientists that are really trying to analyze ground motion, what you'll take is the raw data and you'll remove the effects of the instrument response. So, in addition to having our data up on Iris, we also have instrument response files on Iris so that if a
Hmm.
scientist wanted to use our data for something, they would also know enough about our instrument to be able to remove the effects of all of our electronics. And then once you remove the instrument response, which is basically a mathematical operation, um, then you'll have something that has physical meaning, like meters per second for ground velocity or meters for displacement.
Right. Um, I know when we look at a seismograph in earth science class when we do, because for New York State you have to basically find the difference in time between the P and the S wave, and then go to the
Hmm.
chart and for three different cities and then determine the location of
Yep.
you know where it is.
Hmm.
So, um, I don't. This data sounds a little more complicated than that, but
Well, you still could do the same
mhm,
activity. I mean, that's still essentially what
right,
we do. You still
hmm
triangulate. So that's called triangulation, right?
right.
So if you have your three stations, so in this, am I still sharing?
Yep, you're still sharing.
Okay, so I think we looked at the record section. So this is for the Japan earthquake. So I don't know how easy or hard it is to see if you can make this bigger, but we have S wave arrival is this blue line, and your P wave arrival is this red line. Now these are the stations in Colorado. So this wouldn't be a good set of stations to triangulate with because you would ideally want stations that are kind of around the earthquake. But
hmm
you still would measure distance based on this time,
Right.
right? The time it takes
hmm
your P wave and the time that it takes your S wave. And you still do that same kind of triangulation to
Right.
locate where your earthquake is. The actual, like, how the computer algorithms run is a little bit different. A lot of times they run on grid search. So instead of triangulating, you actually look at a bunch of different possible locations and calculate those times and say, like, okay, would this make sense if our earthquake was here? Would it get to this station at this time, this station at this time, this station at this time? But you still do what we call picking your travel times. So you still look at your little wiggles and you say, okay, what time did that earthquake get there?
Right.
What time did that
Okay.
get here?
That's
Mm-hmm.
really cool.
Yep.
So to be able to do that, um, as far as authenticity
Yep.
of
Yeah,
data,
that's the real deal.
it's the real deal. Um, that's really cool. So a wealth of data, and and do you know of any other specific like citizen science projects? I know we mentioned the Raspberry Shakes. Um,
So the raspberry shake is the only one I'm familiar
mhm,
with. If there is another, just because they really created the only product that is super citizen science friendly. It would be I know that there's been more developments recently with like doing using people's cell phones, like the
mhm,
accelerometer in your cell phone
right.
as a seismometer. So I'm sure there's like different apps that you can get on the Apple Store and you can kind of watch your or on the Google Store, Apple Store, whatever, and you can like watch your cell phone wiggle. You can record the wiggles of your phone. I'm not as familiar with those. The raspberry shakes are cool because they really are kind of like a toy version of a real instrument. Like there's been
hmm
scientific studies on the data quality of raspberry shakes, and there are some really good uses for them. The cell phones I'm not as sure about, but I think people are trying to use them for early warning, like get citizen scientists to download an app and then use that to kind of track earthquake in real time. But I'm not as familiar with those projects.
Very interesting. I
Hmm.
think that the Raspberry Shakes is pretty cool.
Yeah.
Um, say, Volcano Doc, what should you do if you're driving and there's an earthquake?
That's a good question.
Hmm.
It probably depends a little bit. If there's buildings around you, you might actually be safer in your car. So you want to stop. And I always I guess the number one thing is you always want cover. So if your car is the best cover from falling buildings, then you can stay in your car. If you're in the middle of a field and there's no structures around, you might want to get out of your car. right? Because if it's going to protect you from something falling, that's really what you're worried about. A lot of times, earthquakes, if you're standing in an empty field and there's nothing falling on you, an earthquake is relatively harmless. You probably want to brace yourself and maybe get down on the ground. But we say drop, cover, and hold on is kind of the procedure. So cover, hold on to something if you can.
Yeah. So it's not like in the movies where you're driving and the giant fissure opens up in front of you and you have to like brake before you slide into it. No, no,
Not usually.
no,
Um, also,
no.
actually, that reminds me, I think there was one other question that was in the chat earlier that I don't know if somebody asked about a fault
Oh, he has
and
commented that he lives on a fault, but he
and never
never
had an earthquake.
had an
Yeah,
earthquake.
not all faults are active. Not all faults have earthquakes on them. So I thought of that because what you're describing is kind of
Mhm.
like in the movies, it's like a fault just opens up in front of you.
Yep.
I mean that can happen. You can have liquefaction, which is when the ground kind of turns into quicksand a little bit.
Hmm.
And you can have you can have sinkholes. So you're not necessarily 100% guaranteed that you'll be like safe in your car in the middle of that open field. I guess I should think more carefully before I recommend that because you can have ground failures of different kinds underneath you. But yeah, you're not usually going to see the earth just like split apart. That's a volcano.
Funny. Uh, yeah,
Yep.
volcano. Doc loves the volcanoes.
Yeah.
So, anyways, we've been here talking for over an hour now. I know it's hard to believe.
Went by so fast.
I know, right? It is constant conversations. Um, and I want to thank you for joining me and all the viewers tonight.
Yeah, thanks for inviting me.
Yeah, and I learned a lot, and I know everyone that's watching did too. Yeah, we're gonna be finishing up here anyways, Volcano Doc. I got to get to sleep at some point. You know, I have a lab we're doing tomorrow, so
Yeah,
I got to get
it's kinda
prepared.
late where you are.
Yeah, it
Where
is.
I'm only at 8 o'clock, so
So we're
well,
gonna
thank
get
you
going.
so much for having me, and,
Thank you.
I think what you're doing is pretty cool, and keep up the good work.
Oh, thank you. We are going to raid, I think, and this is what we do here on Twitch. We go visit somebody else. I think we're going to go raid Diatom's attack because I believe Diatom's attack is uh, is streaming right now. Let me just make sure they're not going to like stop streaming in the next like 5 minutes. They've been streaming for an hour, so I have no idea. But we'll hop over there anyways and see.
Alright.
But I thank everyone for being here, and I should be streaming again. Actually, I won't be streaming Friday. I'm going to a science teacher conference this weekend. So,
Woohoo!
going to Syracuse, New York. Exciting. Um,
Alright, I'm gonna
so,
sign off.
all right.
Have fun in Syracuse.
I will.
Bye.
Thank you. All right. And we're going to head over there right now. And thanks, everybody. It was awesome. And we're going to have more guests on. I'm planning it out. All right. See you later.